And my name's Mark. This is Omar, Terry, Yale, and Nishant. And basically, our original project goals were basically to create this robotic waiter that could go around a dining room and take food requests from diners and pick up the food from the kitchen when it was ready, and then deliver it to the diners. So basically, the things that we wanted to incorporate was path planning to figure out the best path to service all of the requests, obstacle avoidance, taking requests from diners, picking up and putting down the food, having some kind of robotic arm to do that with inverse kinematics, so it could do it autonomously, and building the actual robot platform that could accomplish this, and possibly some computer vision and using indoor localization to figure out our position and orientation. So in terms of what we actually did to accomplish this, we have successful path planning, which finds the shortest path to service all of the requests, and it works by basically making a tree of the possible requests, the possible orders of requests that it could go through, and then finding the least cost path. And we break ties using fairness. So like if one guy orders first, it would prefer to service that guy first. And our robot is running a state machine that's inspired from our work we did in the labs before. And our robot platform is based on the Parallax Eddy. And we have a Lynx Motion arm. We have networking code and a GUI for putting in diner requests and the chef's table. And we have effective inverse kinematics code. We also are using OptiTrack for indoor localization, and we're streaming that to the laptop on the robot. We decided not to use the Kinect for food tracking because it wasn't really necessary, since we could just use OptiTrack. We'll talk more about this later, but it turned out that we didn't actually have enough precision to autonomously pick up food blocks. So in the demo, you'll just see the arm reaching out and then sort of pretending to drop the food in the bucket there. And we also decided not to do obstacle avoidance because we found out that when people are walking through the dining room, we actually don't get data from OptiTrack, since the cameras are blocked and it's pretty sensitive to that. So we decided not to do that. So just like to show you the sort of general architecture, on the robot, we're going to put a laptop on the robot, and that's connected to an Arduino Mega. They communicate serially, and then the Arduino Mega is connected to the robot's actuators and sensors, and we have the diner laptops, OptiTrack, and the kitchen laptop communicating with the robot laptop over Wi-Fi. So Yale's going to talk about the networking.
So all of our networking is between the laptops is done in socket programming in Python, and here you can just see a GUI for the order form for different tables, and these will all be on separate laptops. And in our restaurant, it will be on, like, the laptop will be at a table, so customers can place orders. And we also have a kitchen GUI that can fulfill orders. And yeah.
So I'll be talking about the hardware that we have. So this is our circuit here. You could see in red the H-bridge and in blue the microcontroller. And that's what the whole thing looks like. I'm going to go in a little more detail about each component. So this is the robot, the Eddy platform that we're using. It was ready-made for us, and it has 2 motors, and the arm is placed on top of it. So next slide. We're using the Arduino Mega for the microcontroller. It has more PWM signals than the smaller Arduino, and we're using some of those for the motor control and of the car, and some of them for the arm. This is the H-bridge. It's pretty simple to use. We have the PWM signals inputted from the bottom yellow ports, and then the motors are connected to the top blue connectors, and we have power coming in from the middle. This arm is a 4-degree of freedom arm, and it has servos that send a pulse signal. We use the Arduino Pulse library to control it. And this is a short video of the arm picking something and dropping it in the box. So this is our kinematics model. We have 3 links and 3 angles. And we simplified it by setting the last link to be always horizontal. So it's not over actuated, and we have exactly 2 unknowns and 2 equations. These are the equations that we get. The first one is gotten using the cosine rule of a triangle, which is not that difficult. And then 2 more inverse trigonometric relations, and then we're done. We can get all the angles we want. We've plotted the reachable space of the arm in MATLAB in order to know where we could reach, and the values you could see here are in centimeters. The horizontal axis is for radius, and the vertical axis is for height. And Yale's going to talk more about the OptiTrack system.
So for localization of our robot, we are using OptiTrack. So the OptiTrack system gives us 7 quantities. It gives us the X, Y, and Z coordinate, and also 4 quaternions that are used to compute Euler angles. This is streamed from that workstation using VRPN, and then streamed to our robot laptop using UDP. And we have encountered some troubles with network lag that we'll talk about later.
So for the robot path planning, what it essentially does is takes the dyno requests that it has to service, and it figures out the shortest distance possible and services them. So it essentially prioritizes first by distance, and then the second optimization would be order that the requests are placed in. So the additional advantage of our path planning algorithm is that it allows for dynamic updates, meaning that while the robot is traveling, you can give it requests from a table, and it will re-update the path accordingly, and possibly even a new path if that is the shortest path possible. So what it basically, can you go back actually? So essentially what it does is it's a tree which calculates all the possible paths, and it figures out the least possible distance among those. Once it does that, it figures out what the next best path is based on what we call fairness. So if a table, for example, 4 orders before table 1, then instead of going from chef's table 1, 4, chef's table, instead it'll go chef's table 4, 1, chef's table, because 4 ordered before 1. Go ahead.
Okay. Hello. All right. So the problems we encountered when trying to implement all the details. First of all, the OptiTrack streaming was not very reliable. If, like Mark mentioned, someone walks while the OptiTrack is streaming data, then we'd probably lose the robot. Second, there was a pretty long latency when we were trying to implement the networking code with TCP protocol. So we changed it for UDP for lower latency. So in OptiTrack, it has a different coordinate system than we do, so we needed to adjust our coordinate system, and that complicated a lot of the calculations, especially for the arm to pick up the objects and calculate the angle and radius. The robot motors on the parallax eddy board, we initially wanted to use encoders because the forward motion was not entirely reliable. especially with the two smaller wheels that control the turns, it sometimes just get in the way of the forward motion in specific situations. So we just needed to ramp up the power going to the motors for more reliable movement, and we did not get the encoders to work. So we just relied on the path planning code to correct for any errors that the wheels would give us. And in our demo, we're not going to have the robot arm actually physically pick up anything. It will do the motion because all the inaccuracies in each component of our system will add up. So then the arm will not reliably always go into the right position. It will probably go in the general vicinity. It will be off by a few centimeters, but the accuracy was not enough given our constraints and our implementation. And a huge problem with software version control, Dropbox isn't the best. Next slide. And for future work, if we had more time, we'd probably get a better means of localization so that we would allow more foreign objects in. Apparently, if we had more cameras, that might have been possible. It's just that if someone were in the area, I think OptiTrack needs at least a few cameras to be on the robot. So if someone was in the area, maybe one or two cameras would be out, and then we just lose data completely. We'd probably want to get the encoders working. If we had more time, we try to integrate everything together in I think the last week. So we didn't have enough time to get that fully working. We just made a design choice to just go ahead and let the path planning code correct for it. And maybe if we had more time, we'd also be able to implement the Connect so that we can detect the food objects and have more precision when picking up the blocks up, or the food blocks up, to give a better presentation demo. And in terms of software, I think we can improve the scalability to allow multiple diners in the same space. I think our demo, it gives the basic functionality of what a robot waiter should be. And maybe, obviously, in the dining room, there'd be more than one waiter, and we could just increase the scale.
And then this project wouldn't have been possible without the help and support from various people. So we just want to say thanks to the department and the professors and Zach and Winthrop for providing us with OptiTrack to use and allowing us to buy the robotic arm for our project. And thanks to Dorsa for mentoring us and helping us with OptiTrack. And thanks to the professors and Zach and Jeff for the labs, which were helpful in preparation for the project. And thanks to the calligraphy team for sharing OptiTrack with us and collaborating on the streaming code. So we're going to do the demo now. And just to kind of explain what's going on, basically, that box there is the chef's table where food that's ready to be brought to the diners is placed. And then each of these squares are diner tables where the diners are waiting for their food at. So yeah, we're just going to set up the demo now.
The GUI for table 4 loaded, and Mark is sitting at table 1. So what I'm actually going to do is first just create a order for table 2. And these order forms can actually be on different laptops. Just for simplicity, or just for the demonstration, I'm going to have 2 of the tables on my laptop and also the kitchen as my laptop. So if I just place an order for B, or, oh wait, yeah, Terry's not running yet. Sorry. You're not getting data? Oh, I need to be on our own network. Oh, so right here, the kitchen sees an order that table 2 has placed for item B, and it can fulfill this order, and I'll do that once the robot is set up. Is it tracked? All right. So right now I'm going to send the request that order B is ready. So the robot is going to go to the kitchen and use the arm to pick up our imaginary food.
So that's kind of where we wanted the food to be, but the accuracy was not enough to always be able to pick it up.
So our robot does not actually pick up the food to deliver to customers because we would need to know where we dropped the food, and that's a bit complicated. So the food would just be picked up by the customer. So right now we can give it a more complicated order. So I guess we can just do all four. Like Mark can just place an order for table 1.
Okay.
And then I can place an order for table 2 and then table 3. Whoa. Oh, you sent it 2. All right. It's okay. So right now we only have, yeah, sure.
So unfortunately, due to the lack of precision in the arm, we couldn't get the 3 different items that we wanted. Originally, we're going to have 3 different spots on the chef's table, and based on the items, the arm would grab the correct item. Unfortunately, that didn't work out. So in our pathfinding, it basically considers everything B. So that was, I guess you can consider that future work.
So right now the kitchen is going to tell the robot that order B is ready for 4 orders of B already. So the arm will now pick up 4 foods.
So right now, the way that the path planning is set up, it's going to basically make the arm pick up as many times as there are the number of requests it has to service. So as you can see, the arm will pick up 4 times for the 4 requests that were serviced. And then after it does that, it'll start going to each of the tables. One of the invariants that we have in our path planning is that if a table makes a request, the robot will first go to the chef's table and then go to the table to service. In other words, it's not going to go to the table first and then go to the chef's table, since it would be pretty nonsensical to bring it nothing. So
in this robot's path, we can see our fairness being incorporated because the orders were ordered in, one was actually ordered first, but then it was 3 or 2, 4, and then 3. So this is the most fairness because 3 was ordered last. So it incorporates fairness as well as the optimal path.
So in the path planning, the first priority is least distance. So as you can see from here, we have chef's table, 1, 2, 4 chef's table is the equivalent to chef's table, 4, 2, 1 chef's table. So so the additional constraint, or the additional optimization, I should say, is after that. Since we have these 2 equal optimal paths, the robot will consider the one with what is called the least order infractions. So even though table 1 ordered first, table 2 and 4 ordered soon after. So the priority would go to servicing 4 and 2 before 1, which is why it chose to go 4, 2, 1 and not 1, 2, 4. Mark, you want to talk more about that or no?
So basically for the path planning, we wanted a shortest path, but we also wanted fairness. And what we decided was that we really cared more about having the shortest path. So even if it's not in the exact order that it was placed, we decided that it was more important to us for the robot to drive in the shortest path possible. And the fairness only comes in for tie breaking. So basically, as you can imagine, due to the math in terms of the distances adding up in terms of the paths, you can actually get a lot of ties when you look at the tree of orders to fulfill. So basically, when we have those ties, when we see paths that are the same distance, we'll tie break based on fairness, which is basically calculated by a function that looks at sort of how off the order of the requests are from a list that would be the exact order in which they were placed. Unless you want to show any more demos.
guys can basically shout out orders and we'll fill them. And just shout them out anytime. Just pick a number between 1 and 4. Feel free to shout it out.
Actually, I can show like a dynamic order. I don't know if we want to do that for time constraints or. All right, so if right now table 4's order is going to be fulfilled.
So one of the additional things that the robot does is that there's about 10 seconds from when it actually goes and picks up with the arm. Okay, so as you can see, what happened was that Yale put in another order, so it changed the path. That's why it came back to the chef's table to pick up a second item for the next table.
So are there any questions?
I mean, you guys can just shout out orders.
No, I think it's good.
I think we're good.
Yeah. All right, thank you.